Hi everyone, Dr. Burns here with our second lesson in Chapter 7, Molecular Geometry, Intermolecular Forces, and Bonding Theory. In this lesson, we are going to be focusing on how molecular geometry and polarity overlap, as well as intermolecular forces. So let's begin. We just learned about molecular geometries and how the shape of the molecule matters. Now, molecular polarity is one of the most important consequences of determining the molecular geometry. So let's look at a diatomic molecule. Here we have HF, hydrogen fluoride, or hydrofluoric acid. A diatomic molecule is polar when the electronegativities of the two atoms are different, which is something we looked at in a previous chapter, where we used our electronegativity table to find the difference in those values. So we would call this a polar covalent bond. Now, we talked about this in previous lessons when we only looked at two atoms, so diatomics, or we were looking at an entire molecule, but only determined the polarity of the individual bonds. Now that we've learned about molecular geometry and how the shape of the molecule is set up in 3 dimensions, we can now apply what we've learned about polarity to the molecule overall. So, the polarity of a molecule, meaning something that is made up of 3 or more atoms, is going to depend on 2 things. First is the polarity of the individual bonds, which is something we've already done in the past. And then it also depends on the molecular geometry itself. How are those bonds arranged, and how does the polarity of those bonds affect the polarity of the molecule overall? So let's look at carbon dioxide. So if we look at first the polarity of the individual bonds, we want to look at carbon to oxygen. So we see that carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. So the delta En is equal to 1. Remember, when we're calculating the change or the difference in electronegativity, this is an absolute value calculation. We're just looking for the absolute value difference. Because that difference in electronegativities is 0.1, this falls into the second category of being a polar bond. So the bonds in each, for both carbon and oxygen double bonds here, are both polar. Okay, and our more electronegative atom is oxygen, so the electrons are being pulled towards the oxygen, which we denote by an arrow. So the electrons are being pulled towards both oxygens away from the carbon. So now that we know that the bonds are polar, we want to look at the molecular geometry overall to determine if the molecule is polar. Now, we can have molecules that have polar bonds but are overall nonpolar because we have to think about how the molecule is set up. So I'm going to erase our little notation here so we can easily see this. So our electrons are being pulled in carbon dioxide in equal but opposite directions. Okay, these are both oxygens, so they're both being pulled towards the oxygens with equal amounts because the difference in electronegativities for both of these is 1.0. So if we think about symmetry and geometry, if I were to draw a line right down the center, these would be equal on either sides. So the polarity of those bonds cancel each other out. It's like playing tug of war. The electrons are being pulled this way and this way, but with equal strength. So no one's going to win that tug of war. So overall, this molecule is nonpolar. Okay, now if we think back to when we talked about polarity, we said that we could see where electrons were localized on polar molecules. in this one, there's no one spot, in this molecule I should say, there is no one spot that has more electrons than the other. We have high electron density on the oxygens and not a lot on the carbon, so they equal each other out. There's no one spot that we can point to and say that portion has more electrons than another, and it is being shared unequally. So because the electrons are being shared equally, and being pulled in equal but opposite directions, the molecule overall is going to be polar. So our final statement here is that the bonds in CO2 are polar, but the molecule overall is nonpolar. Okay, let's keep looking at this. So for our little review here, I have the molecule CH4, which is methane. And we want to know, are the bonds in the molecule below polar, nonpolar, or ionic? Well, we know it's not going to be ionic. We're going to cancel that one out because we have bonds. If we have bonds and we know that we're between a metal or two nonmetals, then it can't be an ionic compound. So we're really looking for are the bonds in this molecule polar or nonpolar? So we're just going to get rid of that ionic option. It's not going to be ionic if there are bonds. Okay, so let's determine that. So we're looking strictly at the bonds. Since all of the bonds are the same, they're all CH bonds, we just have to look at the delta En of carbon and hydrogen. So carbon's electronegativity is 2.5. There it is on our chart. And hydrogen's is 2.1. There it is on our chart. So that's a difference of 0.4. That falls into our first category. So the bond, the actual bond itself, is going to be nonpolar. Okay, because the electronegativity difference is less than 0.5, the bond itself is nonpolar. Now we're going to take it one step further and say, is the molecule overall polar, nonpolar, or ionic? Well, again, it's not going to be ionic at all. Goodbye. Okay, so is the molecule polar or nonpolar? Well, we said that these are all nonpolar bonds, so it's not like the electrons are being pulled in any way. So they're being shared equally in all of these bonds, and all of those bonds are equal. Okay, we have symmetry, right? I have a line of symmetry here, a line of symmetry there, a line of symmetry there, a line of symmetry there. So because this molecule is symmetric, it is going to be nonpolar. Also, I can't have a polar molecule if it's made up of nonpolar bonds. Oops, I spelled molecule wrong. Okay, so because all of my bonds are nonpolar, the molecule overall is nonpolar. It's also very symmetric, suggesting that it's also nonpolar. Okay, let's look at our next one. So again, to review, are the bonds in this molecule polar, nonpolar, or ionic? We're going to get rid of ionic. We know it's not an ionic compound. It's water. Water is not ionic. So we want to look at the delta En of oxygen and hydrogen. Okay, so we're looking at this bond here. So oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So that's a difference of 1.4. Okay, so that falls into our second category, meaning that this bond and this bond are both polar. Okay, let's look at the molecule overall. So if these bonds are polar, the electrons are being pulled up towards that oxygen, okay? So because they're being pulled and they're not being pulled in equal and opposite directions, they add together, okay? So the molecule overall is going to be polar as well. If you think about it, let's try to draw some here. Shall I use a highlighter? That might be easier. We'll say that blue is low electrons and red is high electrons. So because the oxygen is pulling all of those electrons towards it, it has a lot of electrons over here. Okay? The hydrogen only has one electron to give away, so if the bond is being pulled, or if the electrons through that bond are being pulled towards the oxygen, that creates area down here by the hydrogens where I have essentially no electrons. So this gives me an area of partial positive, right? Because there's little to no electrons there, so it's partial positive, and an area of partial negative. So if I have an area of partial positive and partial negative, that means that we have an overall polar molecule. Okay. Also, if you think about it from symmetry, there's only one line of symmetry there, and those arrows don't necessarily cancel out. I can't draw a line of symmetry there, I can't draw a line of symmetry there or there, so this molecule is not very symmetric, meaning that it's going to be polar. Okay, in our final example, let's determine if the bonds in BCl3 are polar, nonpolar, or ionic. Well, we have bonds, so it's not ionic at all. So we have polar and nonpolar to determine. So let's look at the delta En. Boron is 2.0. Chlorine is 3.0. Again, this is an absolute value, so that gives us a difference of 1.0. That lands us in our second option here, which says that it is polar, so the bonds are polar. Chlorine is our more electronegative molecule, so they're being pulled towards that chlorine. Okay, so now let's determine if the molecule is polar or nonpolar. So we said that the electrons are being pulled towards the chlorines. Okay. So if we again go with our highlighting, we have areas of more negative spots here and here. And we have an area of more positive there. Now if we look at this is a symmetric molecule, right? There's a line of symmetry, there's a line of symmetry, and there's a line of symmetry. And you can also think of these arrows as being pulled in equal but opposite directions. They're all being pulled towards chlorines, but those chlorines are all 120 degrees from each other. Okay, we know our angle from our shape, okay, our molecular geometry. So overall, this molecule is nonpolar. So we can have nonpolar molecules made up of polar bonds. Okay, because what can happen is those polar bonds can all cancel out. That's what we saw in carbon dioxide, and that's what we're seeing here in BCl3. Okay, so let's look at another example of this. This uses vector math. If you're familiar with vector math, maybe that's the best way for you to understand this. If not, you could just look at how the arrows kind of are being pulled, or we can look at electron densities. That's totally fine. There's many ways to visualize this. So my first example, I have CCl3. These are all polar bonds, and again, they're being pulled towards the chlorine, okay, just like our previous example. So we have 4 spots of high electron density and 1 spot of low electron density. Now because this is tetrahedral, all of those bonds are being pulled at 109 degrees from each other. So they're going in equal but opposite directions. I can't really show lines of symmetry here because we're now in 3 dimensions, but you could have a line of symmetry on this plane, And then I can't draw the other plane very well, but there's a few planes of symmetry in this molecule. So overall, this molecule has polar bonds, but the molecule itself is nonpolar. So another example of molecules that have polar bonds overall being nonpolar. If I were to take one of these chlorines and replace it with a hydrogen, well, that changes how the electrons are being pulled. So that carbon-hydrogen bond is now, the carbon is more electronegative than the hydrogen, so the electrons are now being pulled from the hydrogen to the carbon. So if you were to highlight this, we have our electron density focused here on the chlorines and slightly on this carbon, okay? And then we have an area of very positive portions up here where that hydrogen is. So we see an uneven pull of electrons where the electrons are mainly down here with a partial negative. They're focused really down at that bottom, that trigonal base of the tetrahedron. And then there's an area of partial positive right at the top there, okay, because of that hydrogen. So the bonds in this molecule are polar, okay? The carbon-chlorine bonds are polar, the carbon-hydrogen bond is not, okay? And the molecule itself is also polar, okay? So if we have uneven distribution of atoms, maybe they have differing electronegativities, then we're most likely going to have a polar molecule itself. So let's keep practicing. For the following molecules, determine if they are polar or nonpolar, and if they are polar, determine which atom is the most electronegative. Okay, so the first thing we have to do is draw the structure. Okay, so we have to draw our structure for each of these. So for time purposes, I'm just going to draw the Lewis structures. If you need time to draw these Lewis structures with me, feel free to pause the video and use your Lewis structure guidelines to help you along and make sure that your Lewis structures match mine. So here we have carbon, we have a double bonded oxygen and 2 hydrogens. Okay. We then have N2. I'm going to draw the Lewis structures first and then determine our electronegativity difference. So we have N2. This is going to be N triple bond N, and then there's going to be 2 a lone pair on each nitrogen. SiH4. Again, I'm trying to draw these with the semi-accurate looking structures, so they kind of look more like our geometries rather than a 90-degree Lewis structure. And then we have OCS, which we've drawn in the past, and that is oxygen with a double bonded carbon with a double bonded sulfur. Okay, you can have other variations of this, like oxygen single bonded carbon, triple bonded sulfur. You could have multiple different versions of it, but because polarity of bonds is not affected by if it's a double or a single or a triple bond, you can draw it anyway and your answer will still be the same. So let's look at some electronegativities. Because I don't have my electronegativity chart here, I'm just going to write these out. Carbon is 2.5, oxygen is 3.5, hydrogen is 2.1, nitrogen is 3.0, silicon is 1.8, and sulfur is 2.5. Okay, so for our carbon-hydrogen, that's going to be 2.5 minus 2.1. Let me zoom in so we're looking at one structure at a time. So we have 2.5 minus 2.1, so that's 0.4. 0.4, so that's going to be 2 nonpolar bonds. And then our carbon-oxygen, so carbon's 2.5, oxygen's 3.5, that's going to be a 1.0 difference. Okay, we determined that when we did carbon dioxide. Okay, so there's some lone pairs on that oxygen there. So this molecule has an area of more positive and more negative because it's polar in that respect. So this is a polar molecule, and they're being pulled towards the oxygen, which is the most electronegative. Okay, let's look at N2. Now we said when we talked about polarity of bonds, if it's the same atom, it has an electronegativity difference of 0, because you're basically taking 3.0 minus 3.0. That's our electronegativity of nitrogen. So this has an electronegativity difference of 0. So the bond is nonpolar, which means that the molecule itself is nonpolar. Okay. Next we have silicon and hydrogen. They're all the same. So silicon is 1.8 and hydrogen is 2.1. So that's a difference of 0.3. So these are nonpolar. And since they're all the same, the molecule itself is nonpolar. Okay, there's no one area of more electron density than the other. The electrons are all being shared equally in all 4 bonds. Okay, and finally we have OCS. So let's see, carbon, oxygen, that one is 3.5 minus 2.5. So that's an electronegativity difference of 1.0. The carbon sulfur is 2.5 minus 2.5. So that's an electronegativity difference of 0. So we have a polar bond and a nonpolar bond. So our electrons are being pulled towards this oxygen and being pulled away from that sulfur. So we create a partial negative and a partial positive area. So this is a polar molecule. And our more electronegative atom is oxygen. Okay, so we have the electrons being pulled this way. They're being essentially shared in that carbon-sulfur bond. So our electrons are just being pulled towards that oxygen, creating a polar molecule. Okay. Let's do a little bit more practice. So this is so that we can start to visualize our individual kind of molecules and how things are being pulled. Is it symmetric? Is it non-symmetric? Things like that. So which of these molecules are polar? And you should assume that all of these bonds are polar. So that's a polar bond. All of these bonds are polar. Okay, so take a second and pause the video. Think about this problem. Think about which ones are going to be polar or non-polar and why. Okay, so I think our most obvious one that of being polar is going to be this one, because it is the least symmetric out of all of the other atoms or molecules. So if we think about it, if these are polar bonds, we don't know which one is more non-polar, but we can assume maybe the larger of the two atoms are going to be the more polar or more electronegative atom. So we know that we have some portion up here that the electrons are being pulled towards that's going to be more negative, and some portions that are going to be more positive. Now this could be reversed. This could be that, you know, the blue ones are more electronegative, so the electrons are being pulled this way, and that there's more of a positive on that central atom. But either way, it still shows that there's an unequal sharing of the electrons, creating a polar molecule. These other three examples, since we don't know the exact identities, we don't know the magnitude of their polar bonds, so we really only have their symmetry to look at. If we knew the magnitude of how polar the bonds are, we could tell if there's more of a electron density on one atom or the other, but since we don't know that, let's just see if there's symmetry in these atoms. When we know linear molecules are symmetric down the middle, so those two polar bonds are going to cancel out. So these are polar bonds with a non-polar molecule. Okay. This second one here, it has all of the greens are in the same plane being pulled at 90 degrees from each other. So those essentially cancel each other out. And then the two red atoms cancel each other out as well, because they're being pulled in equal but opposite directions. So because all of those atoms, their polarities essentially cancel out, this is also a non-polar molecule. Okay, so that's also basing it off of their symmetries. In this last one, this is a tetrahedral molecule, so there is symmetry within that. Okay, again, we don't know the exact magnitudes of these atoms and their electronegativities, so we can't say if these white ones have more electronegative pull or not for there to be a more polar portion. Okay, so there could be, if we knew that, there could be an area that's more negative versus an area that's more positive, but you would need to know the identities to do that. So basing this strictly off of symmetry, this is a symmetric molecule, meaning that this would be nonpolar. Okay. So now we want to talk about the forces that are between different molecules. So we have two different forces that we're going to talk about. First are intramolecular forces. These were the types of forces that we talked about back in chapter 5. So this is going to be covalent and ionic bonding. Okay, this is even a little bit of chapter 6 when we talked about polar versus nonpolar. So, intramolecular forces keep a molecule intact. So they are the polar or nonpolar or ionic bonds that are between the elements within the molecule. So this bond is an intramolecular force. Intramolecular forces are very strong. It takes a lot of energy to break a bond. More energy that we can put in on our own, okay? The next question is saying, well, what if we put two of the same molecule next to each other? What type of forces would there be between them? And that is called an intermolecular force. In comparison to intramolecular forces, intermolecular forces are significantly weaker. The intermolecular forces are what we are going to focus on here. So, intermolecular forces are attractive forces between neighboring molecules. These forces are known collectively as van der Waals forces. The further apart the molecules are, the weaker the intermolecular forces are. So IMFs is how I denote intermolecular forces. It'll always be inter, not intra. We never show intra as IMF. IMF is always intermolecular forces. Okay, so the intermolecular forces are attractive forces between neighboring molecules. So when I get to a gas, there are no molecules next to each other because they're all moving around. So these basically have no intermolecular forces in gases. In solids, that's when they are the strongest. And then they weaken as they go from liquid and then to gas. So there are multiple types of intermolecular forces, and it all depends on if the molecule is polar, nonpolar, or ionic. So the first type that we're going to talk about are dipole-dipole. Dipole-dipole interactions are attractive forces that act between polar molecules. Okay, because polar molecules have a positive and a negative end, or a partial positive and a partial negative end. So they're acting like our magnets. So they're going to be attracted to each other via their positive and negative sides. Okay, so we see that attraction. The positive of one molecule is attracted to the negative of the other neighboring molecule. Okay, so these are the attractive forces between polar molecules. Nonpolar molecules don't have this because they don't have a partial positive or partial negative to them. The magnitude of this attractive force is going to depend on the magnitude of the dipole. So if there's a very high delta En, change in electronegativity or difference in electronegativity, then we're going to have a significantly higher dipole-dipole interaction. Okay? A special type of dipole-dipole interaction is based off of that high magnitude, and it's called hydrogen bonding. So, hydrogen bonding is a special type of dipole-dipole interaction. Hydrogen bonding only occurs in molecules that contain hydrogens bonded to a small, highly electronegative atom such as nitrogen, oxygen, or fluorine. Okay, so nitrogen, oxygen, and fluorine have high electronegativities. Meaning that when they're bonded to hydrogen, that delta En is large, so it has a large magnitude, and large is a relative number because the delta Ens can really only go from to 4, so high in comparison to others. Okay, so what's happening is they're so electronegative. Those molecules, nitrogen, oxygen, and fluorine, are so electronegative. They pull all of the electrons towards them when they're bonded to hydrogen. Okay, so they make a really, really strong negative pole and a really, really strong positive pole. Okay, and because these atoms are so small, they're at the very top of the periodic table, so it's also that they're small. Okay, well, there it is, it's small. That means they can get really, really close to the neighboring molecule. Okay, their atomic radii are so small that they can get really close. And the closer they are, the stronger that interaction is. Okay, so it's like putting two magnets together. Okay, hydrogen bonding is like if you put them directly next to each other. Dipole is like if you had a few pieces of paper in between them. They're not touching close. They're just far enough away that they're still attracted, but not very strongly. Okay, so this is a very strong intermolecular force because they're very close to each other. Next up, we have dispersion forces, which are also referred to as London dispersion forces. Dispersion is a perfectly acceptable name. And this is just the result of Coulombic interactions between instantaneous dipoles, but this is for specifically nonpolar molecules. Now, technically, everything has dispersion. Okay, because dispersion is a force of proximity. Let me write that. Okay, so if two molecules are near each other, they're going to form this instantaneous dipole strictly because they both have electrons in them and they both have bonds and they want to just repel each other naturally. So it's just a slight change in that orientation of those electrons. Okay, I like to equate it to when you're walking in the hallway. Okay, once classes get out or something, you're walking in a hallway and you're just trying to avoid people, but sometimes your backpack kind of hits each other, so you kind of go the opposite way to avoid that. Okay, that's basically what's happening with these nonpolar molecules. Now, every molecule technically has dispersion because they're all within proximity to each other, except this is specific because this is the only intermolecular force for nonpolar molecules. if we're looking at polar molecules, yes, they have dispersion, but that's not the strongest intermolecular force. That's between two of those molecules because dipole-dipole interactions are stronger than dispersion. Hydrogen bonding is stronger than dispersion. Okay, so it's not going to be the strongest in polar molecules. So we can write that. It's present in polar molecules, but not the strongest. Oops. So you have to pay attention to when a question is asked. You may be asked either what are all of the intermolecular forces present in a molecule, or what is the strongest intermolecular force. If you're looking for the strongest, then you're looking for only one. It's going to be dipole, hydrogen, or dispersion. But if you're looking for all of them, then all molecules have dispersion. If the molecule is nonpolar, that's the only type. If it's polar, then it's either going to have dipole-dipole or hydrogen bonding. Okay, so you got to just pay attention to the wording of problems, whether they're asking for the strongest or all types of intermolecular forces. Okay. The last intermolecular force is ion dipole. And this is specifically for interactions between ions and polar molecules, specifically water. Okay, so our other types of forces, we were talking about two of the same molecules, okay, two like HFs, two HCl's, whatever it is. This is going to be between two different molecules. Because we're talking about an ion and a polar compound, polar covalent compound. Okay, so this is the only one that's between two different molecules. And it's just the attractive force between an ion and a polar molecule. So if you remember a polar molecule, this one specifically is for water, this has a partial negative on the oxygen side because the oxygen is very electronegative, so it's pulling all of the electrons towards it. It then has a partial positive, okay? So this partial negative is then attracted to the positive ion, okay? Just like a magnet. The size of that ion is going to depend on how strong or weak the interaction is. So the smaller the ionic radius, the stronger the attraction is going to be, because we can get in closer proximity. So this Mg2+ can move in a lot closer to that oxygen than the sodium can. Okay, so that's also because this has a 2+ charge, has a stronger positive pull, so it's more strongly attracted to that negative portion of that water. Okay, this is going to come into play in one of our future chapters. I believe it's chapter 8 and 9 that we'll talk about this more specifically, but it is going to be the interaction between two different molecules, an ion and a polar molecule. Okay, so just to review, a nice review page is always good to have, good to write down and record for when you're practicing on your own. So a dipole-dipole interaction is an attractive force between polar molecules. Hydrogen bonding is a special type of dipole-dipole interaction, but it's only between molecules with hydrogen that's bonded to a nitrogen, oxygen, and fluorine. Then we have dispersion forces, which is an interactive force between nonpolar molecules, and technically all molecules have dispersion forces, but this is the only type for nonpolar molecules. And then we have ion-dipole interactions, which are attractive forces between an ion and a polar molecule, so two different molecules. Okay, so let's practice. What kind of intermolecular forces exist between PCl3 molecules? Okay, so if I were to put two PCl3 molecules next to each other, would this be, what type of interaction would we expect? What type of intermolecular force would we expect? The first thing we want to do is we want to draw that Lewis structure. because we want to know if the molecule is going to be polar or nonpolar, and we have to determine if the bonds are polar, what's the molecular structure, and so on. So draw the Lewis, then determine delta En for the bonds. And that will then help us determine if the molecule is polar or nonpolar, which then tells us the intermolecular force. Okay, so take a second, draw that Lewis structure of PCl3, figure out if those bonds are polar, and try to figure out your answer for this problem. So the PCl3 Lewis structure, we drew it a bunch of times in one of our previous lectures, so maybe you just remembered it. It has PCl3, those chlorines have lone pairs on them, okay, and then there's the lone pair on the phosphorus. That's the important part here, is that there's a lone pair on the phosphorus. If you just took this and drew that, because you saw PCl3 and you thought, okay, we're good, then you didn't notice that, one, you didn't have an octet in your phosphorus, and also you were missing out on a couple electrons there. So make sure that you are drawing your Lewis structures following our rules. So we have PCl3, we have 3 bonds and 1 lone pair. So this is going to be, let me see if I can draw this a little bit more lifelike. Okay, so it's the molecular geometry is trigonal pyramidal, so it's out of plane triangle. Okay, the bonds themselves, that difference in electronegativity is 0.9. Okay, so these are polar bonds. The electrons are being pulled towards the chlorines. So those chlorines have a lot of negative around them, meaning that phosphorus in comparison does not. So we have a polar molecule. Oops, helps if it's a pen, not a highlighter. Typically, if you see a lone pair on a central atom, you're typically going to have a polar molecule. Okay, so if it's a polar molecule, what kind of intermolecular forces exist in PCl3? Well, we know dispersion is going to be there, so that's 1. Because this is a polar molecule, we then have either dipole-dipole or hydrogen bonding. There's no ion present. I'm not saying that there's a PCl3 with another ion, so we can get rid of ion dipole because there is no ion present. So now we have to determine, well, is there hydrogen bonding? Well, there's no hydrogen in the molecule. There's only chlorines. So goodbye hydrogen bonding. This is just a typical dipole-dipole interaction because it's a polar molecule. My next question asks, if the molecule was pH3, would it hydrogen bond to other pH3 molecules? So instead of PCl3, what if it was, okay, so still polar, so it's still a polar molecule, but would that change from dipole-dipole to hydrogen bonding? Hopefully you said no, because there's no nitrogen, oxygen, or fluorine attached to that hydrogen. So just because there's a hydrogen and it's a polar molecule does not mean it's going to have hydrogen bonding. The hydrogen must be attached or attracted to an oxygen, a fluorine, or a nitrogen only. If they're not there, then it's not hydrogen bonding. If it's polar, then it's dipole-dipole. Okay? So only nitrogen, oxygen, and fluorine will participate in hydrogen bonding. Okay. What kind of intermolecular forces are shown here? Okay, so I'm looking at, these are what the building blocks of DNA. Okay, so what are the intermolecular forces that are going to be present in these molecules? And specifically in this circled area. Okay, so we're specifically looking at that circled area. We're looking at here and here, there, there, and there. What types of interactions or intermolecular forces are present there? Because there is a hydrogen that's bound to a nitrogen and it's being attracted to a nitrogen or an oxygen, so here we have a nitrogen and a hydrogen that are bound together, okay? So we have nitrogens that are bound to hydrogens and they're being attracted to an oxygen or another nitrogen, then we know that it's going to have hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole, so if there's hydrogen bonding, there's also dipole-dipole. And because everything has dispersion, dispersion is also a valid answer. Now, if I asked you for the strongest type of intermolecular force, that would be just hydrogen bonding, because the hydrogen bonding is the strongest force out of those three options. Okay, let's do some more. Which of the following molecules would have hydrogen bonding interactions with itself and with water? So water has OH, so that does have hydrogen bonding. Okay, and in water we have a partial negative and partial positive. So let's look at interactions with itself. Let's do that one first. Would it have hydrogen bonding with itself? So we're looking for if there's a hydrogen bound to an oxygen. So we have an oxygen bound to a hydrogen. Okay, they're bound together. Therefore, yes, it would have hydrogen bonding with itself. If I put two of them next to each other, there would be hydrogen bonding between that portion of the molecule. Our next one, all the hydrogens are bound to carbons. So no, it would not have hydrogen bonding with itself because there is no oxygen bound to a nitrogen, an oxygen, or a fluorine. Our final example does have a nitrogen bound to a hydrogen right there, so yes, it would have hydrogen bonding with itself. So now let's ask with water. Well, if it has hydrogen bonding with itself, it's capable of hydrogen bonding. So if it's capable of hydrogen bonding with itself, it's also capable of hydrogen bonding with water, because water has two spots where oxygen is bound to a hydrogen. So yes, this molecule would also have hydrogen bonding with water, as would our last example. Since our middle example here would not have hydrogen bonding at all, then it can't have hydrogen bonding with water because there is no oxygen, nitrogen, or hydrogen bound to a oxygen, nitrogen, or fluorine bound to a hydrogen in that molecule. Okay, so if it can hydrogen bond with itself, it can hydrogen bond with water. Okay. What I want you to do now is try these. We want to identify the strongest or the main, so we're looking for the strongest type of intermolecular force between two of the following molecules. So I'm saying, like, if I put two waters next to each other or two NH3s next to each other, what would be the strongest intermolecular force? Okay, so to do this, you're going to want to draw out the Lewis structure to see if the molecule is polar or nonpolar. And you're going to want to then determine, based off of that, what molecular force or intermolecular force you're going to do. For our middle or our third examples here for CaO and NaCl, assume that this is with water, not with itself. Okay, so for CaO and NaCl, assume those are with water. What is the strongest intermolecular force with water? Just for those two. Our first example is H2O, also known as water. So water is O, H, H. There we go. It's polar. It has oxygen-hydrogen bonds in there, so this would be hydrogen bonding. Okay. Next up we have NH3. So that Lewis structure is NH3, and there's a lone pair on top, so it's a polar molecule. There's N's bound to H's, so that would be hydrogen bonding again. CH4 we've looked at many times. Looks like this. That's a pretty symmetric molecule. So if it's symmetric and those bonds are nonpolar, this would then be dispersion because it's a nonpolar molecule. The only intermolecular force that can exist in nonpolar molecules is dispersion. Next up we have CH3Cl, so I'm just replacing one of these hydrogens with a Cl. So we have CCl, H, H, H. The CCl is a polar bond, so the electrons are being pulled this way towards the chlorine. So because that I have a polar area, this is going to be dipole. It's not hydrogen bonding because I don't have a hydrogen that's bound to a nitrogen, oxygen, or fluorine. For CaO and NaCl, I said what are the strongest intermolecular force between that molecule and water. Since these are ionic compounds, we would see this as Ca2 plus and O2 minus and Na plus Cl minus. So those are ions. So if we have an ion interacting with a polar molecule, such as water, this would then be ion dipole. Same for NaCl. Okay. Our last one is CH3OH. So that OH is specific because it's CH3. That O is bound to the carbon, and that H is bound to the oxygen. That hydrogen has no other place to be but on the oxygen for octet purposes. Okay, so that's our molecule. We have an area where there's an oxygen bound to a hydrogen, so this would be hydrogen bonding. And finally, we have F2, which is just F bonded to F. We remember that if it's two of the same atom, this has an electronegativity difference of 0, so it is nonpolar, so the only type is dispersion. Okay, so those are our strongest types of intermolecular forces. We have to draw the Lewis structure, determine if it's polar or nonpolar, and then from there determine the force. Okay, so how does intermolecular force affect our boiling point? Well, what is boiling? That's going from a liquid to a gas. So we're going, remember gases have no intermolecular forces. So we want to know the boiling point is essentially how much energy we have to put in to overcome those intermolecular forces. So the stronger the intermolecular force, the higher the boiling point is going to be because more energy needs to be put in. So we have a list of our strongest to weakest intermolecular forces. So ion dipole is the strongest because that's between a purely positive cation or negative anion and a polar molecule, so the interaction is really strong. Then we have hydrogen bonding because that's between two polar molecules, but again, they're really small, so they can get in really close and they can essentially have a really strong interaction. Then we have dipole-dipole, which is just basic positives and negatives on the, or partial positives, partial negatives being attracted. And then dispersion, there's no charge involved, it's the weakest, okay? It's a very weak attraction. So the stronger the intermolecular force, the harder it is to separate two neighboring molecules, which is how we go from a liquid to a gas, right? If I have a liquid, my beaker here, okay, I have neighboring molecules all around each other. Okay, so I want to take one of these and bring it out of solution, meaning I have to overcome that intermolecular force. So the stronger the intermolecular force, the harder it is to separate those two molecules from each other. Okay, so we see this trend here with H2O, HF, NH3, and CH4. These are all capable of hydrogen bonding. Alright, sorry, that's wrong. Let's see. There we go. There's our hydrogen bonding. Okay, so those are really high in comparison to everything else, whereas we have CH4 down here, which is just dispersion. So it has a low boiling point. Okay, it's really easy to get CH4 from a liquid to a gas, whereas water takes a lot of energy. Okay, that's why when we're cooking our pasta noodles, the water sticks around for a while because we have to put in a lot of energy to go from a liquid to a gas. Okay, and kind of everything in between here is capable dipole for the most part. Okay, so they have higher boiling points relative to the others. I should say this goes down here. This row is all dispersion because they're symmetric. So okay, so we see that our hydrogen bonding have our highest boiling points and our dispersion have our lowest. Okay, so let's practice that. For the following molecules, put them in order of increasing boiling point. Okay, so we want to go from lowest to highest. Okay, so lowest to highest. So our highest boiling point is going to be the one with the strongest intermolecular force. And our lowest is going to be the one with the weakest. So we have to look at each of these and say, okay, what are the intermolecular forces? So we have HCl. Okay, we have H2.1 Cl 3.0, so that is a polar bond. It's 0.9, so that's polar. It's not hydrogen bonding, so this is going to be dipole-dipole. Next up we have H2O, which we know already does hydrogen bonding. So it's polar, hydrogen bonding there. And our last one is SiH4. Okay, that's going to be a non-polar molecule. So it's going to have dispersion. Okay, so if we want to put it in order, our weakest intermolecular force is dispersion, so that would come first in our lineup. I'm putting number 1, meaning it's going to be first in our answer. Okay, so SiH4. Then comes dipole-dipole, so that's going to be second in our lineup in our answer. And then our strongest is hydrogen bonding, which is going to come third. So we want to look for one where SiH4 is first, so that gets rid of these 3. So I'm left to B and C. Second, I'm looking for HCl and then water, so our answer is C. Okay. So a question I get often is, what if they have the same intermolecular force? What if I have 2 molecules that have the same intermolecular force? How do I determine the boiling point? Well, in that case, boiling point is determined by weight. Okay, the heavier the molecule, the higher the boiling point. And if you think about it, it does make sense because we're trying to take a molecule from a liquid and make it into a gas. So because it's heavier, it's going to take a lot more energy to bring out of solution as opposed to a lighter molecule. Okay, so we first look at our intermolecular forces, because those are going to be our first ranking of boiling points. And then if we have two or more molecules that have the same intermolecular force, then we look at their masses or their molecular weights. And we say, okay, which one's lightest? The lightest one is going to have the lowest boiling point. The highest one is going to have the highest boiling point. Okay, so let's do a little bit more. So what I want you to do for these two examples is arrange them in order of increasing boiling point. So we have lowest to highest. Okay, so arrange these in order of increasing boiling point. So we're going to look at first our intermolecular force, and then we're going to look at our, I shouldn't say mass, I should say weight. Okay, so take a second, look through those two examples and try to put these in order of increasing boiling point. Our first example here is one where all the intermolecular forces are the same, so we have to just look at their masses. So we have F2, Cl2, and Br2. So they all have dispersion. Okay, so since they all have the same intermolecular force, their boiling point is going to be dependent on their mass or their weight. So fluorine is the lightest, so it's going to have the lowest boiling point. It doesn't take as much energy to get that light molecule into a gas. Bromine is the heaviest, okay, so it's going to have the highest boiling point, and chlorine is going to be in the middle. Our next one is going to be based solely off of intermolecular force, because we have CH4. Okay, we have C2H6, so C2, that's going to be our two central atoms, which we practiced drawing when we started doing Lewis structures. So we have C2H6, like that. Okay, and then we have CH3OH, which we drew on a previous slide. We said that this one has hydrogen bonding. Okay, so we know that that one has hydrogen bonding. Our other molecules don't. They all have carbons bound to hydrogens. Okay, so our highest one automatically is going to be CH3OH because it has hydrogen bonding, and that's the strongest. The other two are nonpolar, so they have dispersion. So since they have the same intermolecular force, we now look at their masses. So CH4 is lighter than C2H6, so it'll have the lower boiling point of those two. Okay, so we're mixing intermolecular force and weight in this problem. Okay, so which substance in each of the following pairs would you expect to have the higher boiling point? Okay, so look at these examples. This is similar to what we did, only we're only looking at two. Okay, look at these two and think about which one would have the higher boiling point. In our first example, we have O2 and Cl2, so they both have dispersion. If they both have the same intermolecular force, we just have to look at the heavier of the two. So Cl2 would have the higher boiling point because It's heavier. Our next example is HF and HI. So we have HF, which is capable of hydrogen bonding because it's a hydrogen bound to a fluorine. We then have HI, which even though it's a hydrogen bound to something, iodine is not one that can participate in hydrogen bonding because it's very large. So this is still a polar molecule, so this would just be dipole. So because HF has hydrogen bonding, that's the stronger intermolecular force. So HF would have the higher boiling point because it has the stronger intermolecular force. Okay, then we have F2 and LIF. So this one takes a little bit of thinking involved because you have to remember that LIF is ionic. So if it's ionic and we're talking about boiling, that's going to be an ionic substance in water. If we're boiling something, for right now, for where we're at in chemistry, we're thinking of our solutions as being in water. We don't know any other type of solution, so we're going to think of water. So if I have an ionic compound in water, our intermolecular force is going to be ion dipole because the Li plus F minus are interacting with the polar H2O. F2, we've said previously, is just dispersion, okay, because it's symmetric. There's only two of them. Their delta ENs is 0, so it only has dispersion. So we would say that LIF would have the higher boiling point because of the stronger intermolecular force. Okay, so you have to give it a little bit of thought. Think about what the actual situation is. If we're trying to boil something, it has to be in solution, and if it's ionic, then that solution has to be water. Okay, so just keep that in mind. For our last set of practice here, I want us to think about intermolecular forces and attractive forces and how we see them in our everyday life. So what kind of attractive forces or intermolecular forces do we have to overcome to do the following? If we want to melt ice, if we want to go from a solid to a liquid, an ice, so H2O, what type of intermolecular forces do we have to overcome in order to melt ice? Well, I'm separating the molecules. I'm separating them. I'm going from super close proximity in my solid ice to still in close proximity and touching each other in a liquid, okay, but they're not as close, okay? So we have to overcome first our dispersion force, right? We're changing our dispersion force because they're in close proximity. But the main one with water is going to be or hydrogen bonding. When they're super close together in a solid, that hydrogen bond, those atoms are super close to each other. So that attraction is really, really strong. We have to overcome that. We have to start lessening that attraction in order to go from a solid to a liquid. Hopefully by this you're seeing why water is everything in life, okay? Because it has this super strong hydrogen bonding. What if I wanted to boil molecular bromine? What does molecular bromine mean? That means Br2. And the same goes for solid iodine. That's I2. So what I want you to do is think about these two examples, boiling molecular bromine and melting iodine. Think of what intermolecular forces you have to overcome in order to do that. The only intermolecular forces that are present in both bromine and iodine are dispersion. So those are the only attractive forces that we have to overcome. Okay, So that finishes our second lesson of Chapter 7, talking about intermolecular forces and polarity. Before you move on to your next lesson, make sure you go through your ALEKS homework and master this topic before you move forward.